continue with the remaining part of the photopolymerization processes. We were lastly discussing the fundamentals of actually kind of modeling, or you have some primitive equations between some variables, some parameters, and you'll have some comments on them and try to understand at least the basics of this photopolymerization process. And if you remember, I had gone through this table and this modeling, let's say, part. We have some variables like curing depth, which is highly important. It affects directly the quality of your part, whether it is cured or not, whether the layers are stick together or not. So this is one of the most important parameters, and it's affected by other parameters. And then we have depth of penetration. This is kind of a property of the resin material, and it's the 37% of the irradiance at the surface. So we have the maximum irradiance at the surface, obviously, due to the light or laser, some sources, and the 37% of it will give us the depth of penetration. And then we said that there are some parameters about energy, and the amount of energy given on this resin is called as exposure. And we have a critical exposure value. This is one of the, again, most important parameters in this modeling part. This is critical exposure, and once your energy level is more than that, then curing will start. You will be able to polymerize your resin. And then we have peak exposure. Irradiance is the radiant power per unit area. It depends on the type of actually source you are using. We have output power. We have a speed of the laser or speed of other things if you are using, but it's only mostly valid for laser. And then lastly, we have the radius of the laser beam. So now let's have a look at some basic relationships. The first one is about radiant power, or we can say that it's irradiance of the laser per unit area. And this is our irradiance equation. If you look at here, we have some parameters. What are they? First of all, this irradiance depends on the output power, which means that if you use a more powerful laser, then your radiance will be higher. But what about the radius of your laser? If you keep the power the same, and if you increase the size of your laser beam, then that means you're going to decrease the irradiance with the given configuration, which means that it will be difficult to cure, and it may take more time to do the curing operation. We have some obviously distribution for the X and Y coordinates. So let's have a look at here. Assume that this is our laser beam, and at the center we have the maximum. You can check it by simply using X equal to 0 and Y equal to 0. But once you go outward, it will be decreased. So the maximum radius is at the center. Another thing, if you use a larger, let's say, beam, if the power is the same, if you keep PL constant and increase the radius, then that means your irradiance will be decreased. And then we have the exposure. As I mentioned, this is energy applied on the resin, and this is highly important. If this energy value or exposure value is reaching to a critical value, then that means the resin is cured, and you may go on with the remaining part of your resin. So let's have a look at the equation here, how we calculate the exposure. And again, we have the power of the laser, radius of the laser beam, and this time the speed of our laser. Furthermore, we have the depth of penetration. As I mentioned, this is a property of our resin material, and speed is highly important. Can anyone tell me the relation between the speed and the exposure? So what happens if you go faster? If you go faster on a, let's say, assume that this is our resin. If you go faster, what would happen? Or if you go slower, which one do you prefer in which cases?
We spend the same energy, but for a bigger unit area, for bigger area, if we increase the speed.
Yes, if you increase the speed, then your energy will be distributed. And what about EC? Can you reach EC easier with high speed? Or to reach EC, do we prefer low speeds with the same, let's say, laser?
Low speed.
Yes, if your laser is not that powerful, you should adjust your speed so that you'll be able to actually supply enough energy on this region so that the resin underneath will be cured easily. But if you go faster, then EC will not be reached and the resin will not be cured. So this is a critical thing actually, and it directly affects the fabrication time of your part. Assume that this is a kind of a slice, and if you remember in the CAM software of SLA printer, we had such patterns, right? We had shells, we had shells and kind of zigzag patterns inside, right? Since we said that we cannot have infill percentage and the interior should be filled completely. And that's why the laser actually should scan the whole region in a shorter time so that the overall manufacturing time will be decreased. But if you use a slower speed, then maybe you need to wait for hours to complete a simple fabrication process. But in order to increase, let's say, the scanning process, you need to have required power, obviously. This is important. If your laser is not powerful, then for sure you need to slow down. There are such relationships between laser power, speed, and critical exposure. Any questions, guys, on these simple relationships? The derivations are in the textbook, and I forgot to tell, but you have the second homework. I think most of you have seen it. I don't exactly remember the deadline, but it's on the ODTÜ class for about 10 days. You should be solving 2 problems, which are from our textbook, and you may need to go into the details of these equations, okay? I'm not going to spend time on derivation here. Another thing is about the curing depth. Since I said that this is one of the most important parameters, curing depth. This is the depth of curing as shown here. And this is a typical actually region or cross-sectional shape of our cured line. So what do you think in this configuration? Is our laser moving in X or Y direction? Is it moving in X or Y? So we have a laser moving on the table, and this is curing the resin while moving. And what do you think? In which direction can we have such an cross section?
X direction.
Yes, you're right. Since this will be the movement while it's moving, it has a kind of a, let's say, I'm trying to draw it. We have a kind of a laser beam here, and due to the thermal effects, you have such a region cured. But if you move in Y direction, obviously you have a kind of an rectangular cross section. So in this configuration, our laser is moving in the X direction. Now let's have a look at how we determine the curing depth. As I mentioned, we have a parameter. We have the property of resin. This is penetration, depth of penetration, and it's a resin parameter. And then as you see, we have logarithm here. This curing depth depends on, again, obviously, our laser power. So if you have a powerful laser, as this relation implies, we will have, let's say, might have such an curing depth for, let's say, if PL, let's say, 2 is larger than PL. And what about other issues? This is radius of our laser beam. So if you increase it, then what will happen? We will be decreasing the curing depth. So if you have a larger, let's say, laser beam, then our curing depth probably will be around here. And this is a thing for, let's say, W 0. Let's say 2 is smaller than W0. Okay. This is it. What about the speed, the scanning speed? It has a similar effect like the beam radius. And if you go faster, obviously, then that means you will be curing less amount of material and CD will be decreased once again. Another issue, if you have less, let's say, critical exposure, then your CD will be increased. So what do you think is that? Can anyone tell me the relation between curing depth and critical exposure? So if you look at this relationship, obviously, if EC is decreased, then CD will be increased. Why is that? Can anyone tell me?
If critical exposure is not reached, the solidification won't start. So if EC value is smaller, it will be easier to cure the material, so depth will increase.
Yes, that's what exactly actually this relationship implies. If you have a lower exposure value, then that means if you're not changing the applied energy, then that means you will be above that critical value, and with the help of it, you will be curing more material than before. That's why we have this parameter in the denominator. But this is a simple relation, as I discussed here, between the curing depth and other parameters. What about the last one here? Is the width of our beam, actually here, width of our cured, let's say, region, line width. It depends, as you see, on the laser beam radius. Obviously, if you have a larger laser beam, then you will be increasing that cross section. And on the other hand, if the curing depth is, let's say, higher, then again, we need to have a larger beam, larger, let's say, cross section. But if the depth of penetration is, let's say, increased, then you will be obtaining a smaller, shorter, let's say, thinner cross section. Since the depth of penetration actually is about the amount of energy we are applying, the easiness of energy going downwards. So if it's high, then that means we will have thinner but thicker layers. LW or line width will be decreased, but the layer thickness will be improved. So this is the relation between line width and other parameters. Any questions, guys, on these equations?
Hocam, what should be the relation between curing depth and layer thickness?
Yes, that was actually a good point. I was looking forward to mention about it. What do you think? Let's discuss it. Should we have an exact value between can CD be equal to layer thickness? Let's say layer thickness is just L.
I think it should be a little higher than that.
So if this is the case, then we will have such an, let's say, another cross section. I'm trying to draw the below layer. That will be the below layer, right? If you have CD equal to the layer thickness. But as you pointed out, it should be a bit higher than the layer thickness. Since we want to go into the previous layer a bit, this is the current layer, and the previous layer should be like this. So what will be the problem if you have this relationship between CD and layer thickness?
Maybe layers are not stick together.
Yes, that will be the main problem. Or they maybe stick, let's say, softly and with little shear forces. You may break it. You may remove layers from each other. So that's why we want to go into penetrate into the below layers a little bit so that they will be stronger. Any questions, guys, about this issue? So now we have another equation. Actually, this is an equation summarizing the resin, and it's called as working curve. And each actually resin has a different working curve. And with the help of it, you can determine your curing depth. But the thing is that you need to know the DP penetration depth of penetration, and critical exposure value of that material. So we can, in summary, say that if you have a power of PL, which is scanning your, let's say, slice at a speed Vs, and if this has a curing depth of CD, then we will have a kind of a critical exposure value EC. And this is a relation between all these parameters in summary. But here now I will show you in the next slide that these two are resin parameters. You can obtain them by doing some experiments. After you got it, then you can comment on the CD value for different, let's say, cases. But this is an example of a working curve. How do we obtain it? We simply apply some energy. We apply different exposure values, and then try to actually measure the curing depth. So for instance, you apply 10 units of exposure. This is it actually, and then measure your curing depth and note it somewhere and do several experiments with different exposure values. And then once you got it, then you will have such a linear line. So, if you have a semi-log plot. This is important, by the way. As you see, on the x-axis we have logarithm scales, but on the y we don't have it. It's linear scale. So once you have such a plot, with the help of your measurements, experiments, you can determine this line. And this line is actually representing this equation here. This is our logarithmic part, and we have linear part. And obviously, this interception will give us the critical exposure value. So why is that? If you, let's say, what is this value? Let's check. 2, 3, 4, 5. This is 5 actually. And if your energy exposure value is less than 5 units, then that means you will not be able to do any curing. Your curing depth will be 0. But if you are more than EC, then you will see that we have some material cured, and you can do some measurements and note it. But this might have done by the manufacturers of the materials. They may provide you such information, and then you don't need to do such experiments. So what you are going to do, you may maybe play with the power of your laser, since laser power directly affects the exposure value. So by adjusting the power of your laser, you may play with the curing depth, which means that you cannot adjust the layer thicknesses. So this is directly affecting this curing depth is affecting the layer thickness. If you can cure thicker regions, then that means you can also do, you can fabricate products having thicker layers. And actually that's why, if you remember the software of our SLA printer, they had only two options: 50 micrometers for the layer thickness and 100 micrometers. They don't have any value in between or more than 100 micrometers, since their laser is not that powerful enough. If you want to have, let's say, 200 micrometers, then you should be using a more powerful laser. Otherwise, you cannot go beyond that value. And as you see, dP is the slope here. So we can say that this dP, penetration depth, and critical exposure values are resin parameters, and they are independent of laser power. But once you know the laser power, by using this working curve, you can compute your curing depth, which, as I mentioned, which is important for the layer thickness. Questions, guys? Okay. So let's focus on now some scanning issues. So we said that in SLA, you are not allowed to have some internal patterns, internal structures. They all must be filled completely. The internal material must be cured, and you are going to have solid shapes. So for that purpose, we need to find actually the proper speed, proper patterns. Maybe the zigzag patterns might not be good. So you need to find some special patterns, and we will discuss these issues now. And we know the speed equation here, which depends on the properties of our actually resin material. And as you see, it depends on the laser power, once again, radius and critical exposure, penetration depth. So once you know all these, then you can find optimum speed, optimum scanning speed for your arrangement. And obviously, if your laser is faster, then you will have a higher photo speed. So this is at new term we come up with, which means that at that speed, at that photo speed, you can do the curing operation. Okay, and you can increase it by having a high power laser or low radius or low critical exposure values. And in the previous slide, we said that you can easily determine these critical exposure and depth of penetration values experimentally. And some companies have special test patterns. So you do curing on these test patterns and then measure the curing depths and plot your working curve. And then once you have that curve, obviously the interception with the x-axis will give you the critical exposure, and the slope will give you the depth of penetration. Once you have them, then you can use this equation to determine the optimum scanning speed or the photo speed. So why the scan patterns are important? Since if you do not have the proper pattern, proper speed, then what we are going to have, you might have a huge staircase effect. You can see like stairs on the side surfaces, and you may have a huge shrinkage. Assume that this is the cross section, and they may shrink, and finally your parts might have such a shape. These edges will shrink after the post-curing operation. So this is another good thing actually you want to have after the print is done. So you need to be careful about the internal patterns, the material, the speed, the laser power. Another issue, once you have shrinkage, obviously you will be developing some stresses, some residual stresses, and this may again result in some problems once you have cracks or some other, let's say, once you use this part in different applications, these residual stresses may cause you problems. And furthermore, you may have some warpage. Assume that if this is the plate, and if you do not arrange the parameters properly, then your tip of your part might actually you may have such a distortion, and this is called as warpage. Or you can also name it sometimes curling is too much, and they are all affected by this scanning patterns or power values, speed values. So that's why they are highly important. Another issue, if you do not set these parameters properly, your layer might be thicker than actually expected. So in summary, you should be careful about these parameters. So people actually worked on these issues and come up with different scanning patterns. This is the first one. It's called as view scan pattern. And on the right-hand side, you can see the pattern. Not that complicated. You have some movements in Y and some movements in X direction. And we have a gap between, let's say, these hatch lines, and this is called as hatch spacing. And it's usually around 1 mil. And 1 mil is equal to, as you see here, 0.02 millimeters, about 25 micrometers. So why do we need to have such a separation between this cured, let's say, lines? Since we want to decrease this internal stresses, we want to decrease shrinkage. That's why actually people offered such scanning patterns. And at the end of the actually printing process, we will always have some uncured resin inside the part. For instance, if you consider here, our laser is not moving over this points, right? And since this fabrication is done in a vat, we have polymers all around, so the ones actually inside this region will not be cured since we don't have any laser going over them. So that's the reason why we have usually around 69 or 68% of the resin is cured, but 2 to 4% is not cured. And the thing about this scanning patterns is that if you do not set them properly, then you will have some shrinkages from different sides, and this shrinkage will result in stresses on different regions, and you will have problems in your applications. And that's why people actually started to work on, as I mentioned, on these scanning patterns. And once they see the issues related with the view pattern, they modify it and they call it as star view scan pattern. That's very similar, but the thing is that the hatches are staggered, so they are not always in the same, let's say, X and Y values. They are staggered so that, like this one, we will be developing less stress and we will not have any distorted corner. So these were the problems of the first pattern offered, and in order to overcome these problems, they modified it a little bit so that they have such a pattern, and this is called as star wave pattern. The only thing they have done is that they moved the upcoming slice a little bit in X direction so that we don't have such openings throughout the, let's say, layers. And furthermore, they also had some, let's say, solutions on the edges. They didn't connect these, let's say, lines to the outer profiles completely. They have retracted it. And this is, now let me show you, this is how they have done it. This one is not connected to the side. As you see here, this is the retracted region. And with the help of it, they decrease the internal stresses. And it's a nice feature. And we were able to reduce the shrinkage somehow by simply hatching, by simply retracting these hatches, these lines from the borders. And obviously this is repeated for the Y axis. This is an example for X, but we also have the same, let's say, patterns on the y-axis. And this is, as you know, staggered. In the upcoming slides for the x-axis, we love to move actually on this region, not directly on the below hatch. We shift it a little bit so that some of the problems will be eliminated. In questions, guys, up to now, up to the discussion of these scanning patterns? So now we have a bit different scanning pattern. This is actually not showing the complete scanning pattern, but you can use this approach, use this idea with the previous ones. And here the idea is that by using a less powerful laser, can we cure the same material? And this is called as, this is actually the abbreviation of accurate, clear, epoxy, and solid scan pattern. So ACs means that accurate, clear, and epoxy, solid. The thing is that if you, let's say, assume that this is a specific region, specific unit cell we want to cure, and in the scanning pattern, what we are doing, we actually pass through the same point 3 times. So that is the first one, let's say. And then in the second one, we probably pass maybe through here. And in the third one, we pass here. So you may go like this first, and then make a return, go in this direction, another return, and go again in the minus X direction. So once you do that, as you'll see, that means you are passing through the same point 3 times. And obviously, once you are on the edges of that region, you will not be able to apply too much energy. And with this approach, you can decrease the power of your laser. You don't need to use a high power laser. You may use a bit lower power. But the thing is that you need to go 3 times through the same point. And this actually is summarizing what I mentioned here. Let's focus on this point. Assume that we are here. This is, let's say, x-axis. And on y, you see the exposure values. Let's see what happens in each pass. This is the first pass, second pass, the third pass. Now you see that this is the amount of actually energy we apply on the point for the third one. For the second one, this is the amount we apply. And for the first one, we apply very little. So let me draw them here. This is the maximum we apply once you go with the third one. This is the second one. And for the first one, we have very little. And if you sum all these, you'll see that the summation is equal to this EP, which is the peak exposure value, which is quite high, and we can cure in a better way, since, as you see, this is the maximum % we can have with a single pass, right? But once you pass 3 times through the same point, you can go up to about 50% more, and will be 150, as you see here. So the summary is that by having such a pattern, special pattern, you can cure more difficult material with the same laser. But the problem is that you need to spend more time. Another issue, you need to use again such patterns, but this time you will be, let's say, going through this same hatch 3 times. But if you do not apply ECS pattern, then that means you will be going through this hatch 1 time. That's enough. But if it's an ACS pattern, you need to do it 3 times. You can also pass 4 times, 5 times, but this will result in, let's say, higher fabrication times. So this is the best value. People have done some experiments and they come up with this value 3. So with the help of it, the problems of curing are further reduced. They have eliminated the shrinkage, internal stresses, and warpage. But obviously, as I said, you cannot just use ACS pattern. You should use it along with weave patterns or star weave patterns. Any questions, guys, about these patterns?
Hocam aynı lazeri kullanarak o zaman thickness'ı arttırabilir miyiz? Birçok kez üstünden geçerek.
Yes, you can do that, since if you look at here, if with a single pass, you have the exposure of 100%. But once you pass 2 times, 3 times, this exposure really increase. And once it's increased, then that means you can satisfy higher E values. So your E value will be much higher than the critical exposure value. And if you remember, let me come to the equations. The curing depth, or here less. If this is actually higher, if with your current exposure value, your critical exposure value will be relatively low, and so this will result in a higher curing depth. And you can even cure actually more, let's say, difficult materials. But the disadvantage, the biggest disadvantage, is that you will spend more time for doing the same, let's say, fabrication. So we have some parameters for all of these, let's say, scanning patterns, and I want to focus just on one of them. Here you see the patterns, process variables for the ACS scan pattern, and this is specifically for the printer SLA 250. I forgot the company, but this is their model. What do they have? They have the layer thickness, and as you see, it ranges in between 0.002 up to 8 inches. And then they have some values for hatch spacing. Hatch spacing is the gap between 2 hatches. This is a gap, and it's called as hatch spacing. And we have hatch overcure, which means that you need to shift your laser a little bit and cure the edges of the hatches, so that again we will be curing the whole hatch properly. We have some other parameters for the coating, recoating option, the blade cap, but they're not that important. Sweeping period, for how many seconds are you going to do the sweeping operation. And this is about the waiting time between the layers. You cannot directly jump to this other layer, other consecutive layer. You need to wait a little, and then later continue with the curing of the upcoming layers. So the thing is that actually we need to be curing more material in that layer before bonding into the previous layer. Otherwise, they will not be penetrated into each other, and we will not have stronger products. So that's why we should be curing more than the layer thickness and have good results. Yes, this is actually the summary of what we mentioned, what we discussed. This is the initial curing depth if you use a single laser, single, let's say, pass. But if you have multiple passes, like 3 passes here, that will be the curing depth you can obtain. As you see, initially it's 0.2 to 200 micrometers, but with 3 passes, you can increase it to 350 micrometers. Any questions, guys? Since we are done with the SLA, the vector-wise or point-wise type of stereotypography.
Hocam bu weave'de de border'a bağlanıyor mu?
I couldn't get your question. In which one is it connected to the board? Can you ask it again? Can you repeat your question?
Hocam duyabiliyor musunuz? Bu Star View'da bağlanıyor gibiydi ya bu layer'lar. View'de de bağlanıyor mu?
I still couldn't get what you mean by joining. In Starry, we have retracted hatches. These hatches are not connected to the boundary, but in the original weave pattern, they are all connected to the boundary. We don't have any gap between the boundary and the hatches. If this was your question.
Evet.
Okay. So now we will be discussing the second type of photopolymerization processes. This is called as masked projection approach. This is totally different with respect to the first one. In the first one, if you remember, we were scanning the layer. We had a kind of a point source or a line source. We were scanning the layer. But right now, in this masked projection approach, as the name implies, we'll be projecting a kind of a mask on the table. So, which means that you don't need to scan. The layer will be completely masked, will completely projected on the layer, and the curing operation will be done in some seconds. Assume that this is our layer, and if you have kind of an, let's say, slice to be cured, if this is a region to be cured, then what we are going to do, we will reflect this image with the help of the mirror, digital mirrors on this plate, on this platform. So once this image actually is reflected, the regions having light, and we prefer to keep this one as white, these white regions will be cured, and the other regions, the black regions, will not be cured. Since you will not have any light on there, these black regions will be liquid, but white regions will be solidified with the help of the polymerization process initiated with the light coming through this projector. Okay, this is the fundamental difference. So what we do, we slice the objects once again, take the images, take binary images of them, and then reflect these binary images on the platform. And just in 3 seconds, usually this curing operation will be performed. And then what you are going to do, you will again lower the platform and cure the next layer. And once you repeat these processes for the number of layers, finally you will obtain your desired shape.